Hey ladies and gentlemen, welcome back. We're looking at digestive system, and specifically we're looking at enzymes and how they're going to help facilitate the chemical reactions that we need to happen in our digestive system. So this is a model of an enzyme. It has some alpha helices and beta sheets. This is actually amylase, but it doesn't really do a whole lot for us in terms of trying to figure out how it works. So we use this model, which is kind of the roundish shape here, and it has a specific opening in order for our substrate or the thing we would like to break down to fit inside of it. So when we look at a specific enzyme, we traditionally used to say that it has an active site, which is where a part of the enzyme is going to be used for the chemical reaction, and it follows the lock and key mechanism, which means that the substrate or the reactant or the chemical that we want to break down or build up, if it's a different type of enzyme, will fit into the active site and it will facilitate the chemical reaction. However, as you can see here, it doesn't quite perfectly fit. So what we've modified this model to is to match what we call the induced fit. So the active site actually changes just slightly to better fit the substrate and allow for the chemical reaction to occur. What happens in order for the chemical reaction to occur, we'll get into in a few minutes. So as I mentioned before, the function of an enzyme is to allow a chemical reaction that might happen in the body to happen a lot more frequently or quickly, to the extent that some reactions won't happen at all unless an enzyme is present. The other thing to note is that these enzymes aren't used up in the chemical reaction. They're just used to facilitate, but they don't get used up like a reactant would. Now, how do they speed up the reaction? It's something that we call activation energy. There's a certain amount of energy that each reaction needs to be put in order for the reaction to occur. It's not like it changes the actual enzyme or the molecules itself. It just lowers the amount of energy that you need to put in to the system. So here's an example. Here's the amount of reactants energy. Here's the amount of products. It's going to go down, but in order for this to occur, you need to get up and put in an amount of energy high enough for it to proceed spontaneously. Now, with the use of an enzyme, as you can see, there's a lot less energy needed in order for that to occur. So how does it actually happen? Well, there's a few different ideas. One is that it actually allows a meeting place for the chemicals to be together. If you're looking at breaking it out, or breaking it down, sometimes these molecules, when they're in the active site, it pulls on the bonds in order to make it easier for them to be broken down, for example, by water. And they also sometimes can actually be part of a temporary bond, but eventually after this happens, the enzyme goes back to its regular form. So those are just a few ideas. The easiest one to think about is kind of like a non-inflated balloon. When you squeeze the balloon, it's a lot easier to pop than when it's not inflated. So there are some other things that can actually affect enzyme activity, and one of them is the amount of the enzyme itself or the amount of substrate. If you increase the amount of reactants in an area, it's more likely to join up with the enzyme around. If there's more enzyme, it's more likely to bump into the substrate and allow the chemical reaction to occur. So a nice easy one. The next one is temperature. Temperature is going to affect the amount of enzyme activity, and just as a heads up, all of our enzymes have optimal conditions. So if your optimal condition is temperatures right here, let's say it's 37 degrees. Anything below that, it's not going to be quite as good because the temperature impacts the amount of collisions, the amount of kinetic energy. So as you're increasing the amount of energy, it's more likely to bump into each other until it gets to the max. At the max, they're like, yes, all is good in the world. And as you go over that optimal temperature, what happens is that the enzyme itself can start to unravel. If the temperature is too high, those bonds break and it's no longer able to be able to house or fit that specific substrate, so it starts to go down. This is not necessarily fixed for all enzymes. Some enzymes might work better at lower temperatures and some might work better at higher temperatures. The next one is for pH. So pH is a way for us to, it's a scale for how many hydrogen ions essentially are in a solution. Once again, there's an optimal pH, and it can change quite drastically depending on the enzyme. For example, pepsin that works in your stomach likes a pH around 1.5 to 2, whereas maltase likes it closer to 8 in the small intestine. So as you're coming up here towards our optimal, anything below a low pH means lots of or more hydrogen ions, and they can interact with the different molecules in the enzyme and allow it to essentially break its bonds and start to denature. Also, as you go over the other side of your optimal pH, this means that there's going to be less H pluses or more OH or hydroxide ions. And the issue is that once again, those hydroxide ions can interact with the enzyme and prevent it from maintaining its shape. Another way that we can impact enzyme activity is through inhibitors, another molecule that impacts whether or not a substrate can join to the active site. So here's one, and it's called a competitive inhibitor for obvious reasons when you see it. Here is your enzyme, this little triangle is your active site. This substrate should be able to fit easily inside. However, this inhibitor, if it gets there first and joins, now it's competed for that specific spot and won, and the substrate cannot get in there and be broken down. So that's a competitive inhibitor. So it blocks the site of the active site so the substrate can't join. And you can compare that with a non-competitive inhibitor, which no longer competes for the same active site. As you can see, this has your little triangle wedge, this one has your circle. This circular inhibitor joins to a different spot, and it's called an allosteric site. This allosteric site means shape change. When it joins, it changes the shape of the active site so it no longer fits this substrate, which means it can't be used to be broken down. So both competitive and non-competitive lower the reaction rate of an enzyme, but they do it in two different ways. Now, not all of the different things that happen are going to negatively impact the enzyme activity. Cofactors are one where they can actually join to the allosteric site or the active site to better fit the substrate. So in both scenarios, they're going to increase the rate of enzymatic activity. So vitamins an example of this. If you're taking specific vitamins, the reason why is you want the enzymes that they're going to join to behave and increase the rate at which they're working. Okay, so here's some other ones. So the major ones we know are organics, like vitamins, heme, flavin, and then non-organics like ions, calcium, magnesium, copper. Okay, so that's the main background information you need to know about enzymes, specifically that there's active sites, that they follow a lock and key and induce fit, and there's specific factors that can either negatively impact or positively impact the reaction rate. And that's what you'll need to know for moving on into digestion. Have a great day or night.